This first learning outcome is all about definitions. So current, in general terms, means a flow of charge. Okay, usually a flow of electrons, but in numerical terms, its value is the charge flowing per second. Or in equation terms, I equals Q over T. Even if that's written in the formula sheet as Q equals IT. Remember, I talked about using formulas to help you with the definition. So charge per second. Voltage is the energy transferred per unit of charge. Or in equation terms, V equals W over Q, even if that's written as W equals QV, or even EW equals QV. But often we refer to a supply of voltage is referred to as an EMF, which stands for electromotive force, a kind of historical term for it. And when voltage is used up, okay, so when energy is transferred from the circuit to an external device, this is referred to as a potential difference, or PD. Now, problem solving in circuits, so the formulas are still the same as they were in that 5. So to remind you, you've got stuff like V equals IR, P equals IV, which is also equal to I squared R, V squared over R. And then you've got your rules for series and parallel circuits. So in series, resistances add up. In parallel, it's the inverses that add up. And remember, that works out 1 over RP. You've got to remember that final step of working out RP. Those are given in the formula sheet, but the following rules are not, so you need to memorize these ideas that in series circuits, the current is the same at all points. There's only one branch that can't go anywhere else. Whereas in a parallel circuit, current adds up, so the current in the 2 branches adds up to the main line current, the current coming from the battery. And for voltage, it's the opposite. Voltage in series circuits adds up. The energy is used in one device after another, one component after another. Whereas in a parallel circuit, each circuit is independent, each branch is independent of each other. So there's no using up of energy before they reach the components in that branch, so those voltages are equal to the supply voltage. There's no splitting of voltage. But I'll maybe highlight them in slightly different colour. They are not given in the formula sheet, so you need to memorise them. And other than that, it's just lots of problem solving. So we'll do some worked examples based around these formulas. So in this circuit, the voltage is fixed and we're looking at different possible resistances. So we'll concentrate on the P equals V squared over R formula. And basically that will help us identify the low, medium and high power. But basically, because the R in the bottom line, the V is fixed in this example, then a bigger resistance is going to mean a smaller power. So we'll start with a 30 ohm resistor first of all. So for R equals 30 ohms, V is 230 volts, P is what we're being asked. P is V squared over R, 230 squared over 30 is 1800 watts. Do a similar thing for the R equals 15 ohms. V is 230 volts, so work out that power. And now we see that with a smaller resistance, we get a higher power. But that's not the highest possible power, because remember, in parallel, if we combine two resistors in parallel, the combined resistance is always smaller than that total resistance. So for both, we've got to do an initial calculation of 1 over Rp equals 1 over R1 plus 1 over R2. I'll mention a shortcut to this at the end incidentally, but so 1 over Rp equals 1 over 15 plus 1 over 30. Running out of space here on the page, but you do that, you get 1 over 10. So 1 over Rp is 1 over 10, so Rp is 10 ohms. V is still 230 volts. Remember, there's no splitting in parallel, right? The voltage in each branch is the same as the supply voltage. P is a question mark. P equals V squared over R. 230 squared over 10 is 5,300 watts. And now we can see all the powers tie in with what we expected. The biggest resistance is low power, so we need to identify these. This is our next step up. This is medium power. And with the two in parallel, with both of them on, we get high power. Now the shortcut I did mention earlier is that in series or parallel circuits, total power, you just add up all the individual powers by conservation of energy. Doesn't matter whether it's series or parallel, so I could just add the 1800 and the 3500, and that would give me the 5,300 watts for the total power. So going back to what the question actually asked me, is for low power, you'd have the 30 ohm element on. For medium power, you'd have the 15 element on. And for high power, both elements on. Okay, it's always important to remember what the question is asking you. So here's a fairly typical problem-solving circuit you might be given. And quite often the problem here is, where do you start? Remember, you're generally wanting to start where you know 2 out of 3 things. Now, I know all the resistances in this circuit, but I only know the voltage at one point, and that is the supply or total voltage. So to start this question, I'm going to have to work out the total resistance to go with that total voltage. But that's how I know that's where I'm going to start. Okay, but that's the only voltage I've got in the circuit. There's more than one way to solve these problems. This is not the only way, but I think this is probably the most straightforward way. So yeah, I'm going to lead up to getting the current, but to get there I've got a wee bit of work. So first of all, I'm going to do 6 plus 4 ohms equals 10 ohms. So basically what we're saying is that there could be replaced by a 10 ohm resistor. But then that 10 ohm resistor is in parallel with that 10 ohm resistor. So my next step is 1 over Rp. Now, if you've got 2 identical resistors, a quick shortcut can be, because 1 over 10 plus 1 over 10 is 2 over 10. I know we simplify that as to a fifth. So Rp is 5 over 1 is 5 ohms. A quick shortcut for that can be that two identical resistors in parallel, their combined resistance is half. So I'll use a slightly different colour just to indicate it, but what we are now saying is that this whole section here has a resistance of 5 ohms. And so lastly, that 5 is in series with the other 5. So the total resistance for this circuit is 5 plus 5. It's 10 ohms. The total voltage is 40 volts. So I can work out the total current, the current coming from the battery. Just V equals IR, 40 equals I times 10, and I get that current. Now that's the current coming from the battery, so that will also be the current then flowing through the 5 ohm resistor. Okay, so current through 5 ohm resistor is 4 amps. I'll then get to this parallel branch, and the bottom branch is 10 ohms, and remember the top branch is 6 plus 4 is also 10 ohms. So it will split evenly at that point. You could go a wee bit round in terms of calculations and say, well, I know the 4 amps and the 5 ohms, so that's 20 volts. So therefore the voltage across that branch is 20 volts, and use that to work out the two currents. But the simplest way would be to say even split of current parallel branches so current so the top branch and the bottom branch would be 2 amps. In the top branch, the 6 and the 4 in series, so it's going to be 2 amps through both of them. That will be the same current. The 2 amps will go through both of them. So current through all other resistors, in this case, is 2 amps. So we've now worked out all the currents, and now we can simply work out all the voltages using V equals IR. So for the 5 ohm resistor, so R is 5 ohms, I we worked out as 4 amps, V equals IR, that's our 5 ohm resistor. For the 10 ohm resistor, I is 2 amps. It's also 20 volts. For the 6 ohm resistor, I is 2 amps. And for the 4 ohm resistor, I is 2 amps. Lots of calculations, simple stuff, but okay, that's just done all the voltages, and now we're just being asked all the powers again. So simplest power formula I would tend to use then is the P equals IV1, but you can do it any way you want. You can do I squared R, you can do V squared over R. So for the R equals 5 ohms, then I is 4 amps, V is 20 volts, it's 80 watts. For the 10 ohm resistor, you wouldn't get such a repetitive example in an SQA exam. They wouldn't ask you to work out every voltage or every current. 40 watts, and so on. So this example, we've got a variable resistor being used as a controller. A technical term for that is a rheostat when it's in series. And we're using that to reduce the voltage to the motor so that it runs at 4 watts rather than 10 watts. And then it's got this bit, assuming the resistance of the motor doesn't change. So what we can do is use the information we have about the motor running at 10 watts. Okay, it would normally run on the 12 volt supply, then we can work out that resistance. So first of all, at P equals 10 watts, we know the voltage. So at that point the rheostat's at 0 ohms and all the voltage is across the motor. So we know P, we know V, we're being asked R. So the formula links them together, P equals V squared over R. So 10 equals 12 squared over R. 10 equals 144 over R. And rearranging that, R is 144 over 10 equals 14.4 ohms. And now we can consider what's going on at 4 watts. And we want to work out the resistance of the controller. But once again, all the information we've been given is about the motor. So we need to start at the motor. There's different ways of doing this. You could work out the voltage across the motor, you could work out the current through the motor. So I'll do it that way, work out the current. So at 4 watts, we know the resistance of the motor is still 14.4, so to assume it doesn't change. So we can use them to work out the current. And then you get I squared, it's 4 over 14.4, and taking square roots of both sides, you get I is equal to 0.527 amps. But we could also do V equals IR for the motor. So now that we know all that about the motor, we need to think about what we know about the controller. Well, it's the same current flowing through both because they're in series. We can work out the voltage by subtracting the voltage across the motor from the total voltage. So the voltage across the variable resistor is 12 minus 7.59. And now we can work out R for the controller. And we get the resistance of the controller. And then for part B, we're just asked about the power in the controller. You've got a choice because we now know I and V and R, so you can use any of the equations. I'll just go with P equals IV A is a fairly straightforward voltage divider problem. It's up to you in any problem, if it's not already defined for you, to define what you want to be R1 and R2. So I'm going to call the 10k resistor R1 and 20k, which means I'm trying to work out V1. You've got to be consistent with the ones and the twos. So V1 equals R1 over R1 plus R2 times Vs. And the k's here in the top and bottom line would cancel out. So if you're using V equals I times R or stuff like that, you do need to be careful with your kilo ohms. But if you're just dealing with ratios of resistances like there, then that's fine. Okay, so the voltage across XY is 4 volts. In B now, we've added another resistor there of 10k. And what we're wanting to do then is to work out the combined resistance of this whole bottom half. So first of all, we've got to do 1 over Rp, or you can use the fact it's two identical resistors just to half it, but and once again, if I work in k's for all of my answers here, then I get the Rp, which is our new value of R1, is 5 kilo ohms. Other than that, it's the same as it was before. So V1 equals R1 over R1 plus R2 times Vs equals 5 over 5 plus 20. So the new voltage between X and Y will be 2.4 volts.